Welcome to a new video. In this video we will discuss another precision circuit which is called a clamping or clamp circuit. We will see how we can determine the required component values for a specific upset or clamping of our circuit. Of course we will see step by step the calculations and also verify these in SPICE simulations. Okay, before we jump to the actual design and also the discussion of the precision clamp circuits, let's first discuss the passive clampers and see what the situation there is. We have two situations or two variations of a clamper, negative clamper and a positive clamper. You see here the positive and the negative cycle of our input voltage V in. This circuit, in a very simple using the passive components, has a one capacitor and one diode. When you have a sine wave input here, which is at peak value Vp, this will be then clamped to the negative. In this case we see here a small error of 0.7 volts because due to that diode. So you go actually almost down to 2 Vp. So minus 2 Vp plus of course again this diode voltage drop. The similar case also happens for the positive clamper. So then you have for the negative cycle that this capacitor will be then charged through this diode, but you lose of course the 0.7. And then you have not that you are exactly at 0 but a little bit lower, and you also not exactly at 2 times the Vp, which is the maximum value for your input, so you also have some error there. So there are some errors. That's the reason also for going for the precision clamper, but this is the discussion before that. So what we have, it is now shifting our signal by a DC level, so you can actually see that this signal, which has a DC level of 0, is now shifted down minus Vp plus 0.7 because of this, again, the voltage drop across the diode. And here it is upshifted, so going up, that's why it's called a positive clamper or positive shifter, and then the value is Vp minus 0.7 volts. The application of a clamper is the restoring the DC level or your bias point in your circuit, so it can be that this is needed in order to get the correct biasing. And for steady state condition, the output voltage or output signal is equal to the input signal but shifted by a DC level as discussed before. You can have, as we see here, the positive and negative clamping. Okay, and this is now the expression for the input voltage as given here. Now the negative clamper, ideally the capacitor is C, it cannot be discharged, so we have of course here some load here, but in ideal case it is not discharged. Then the capacitor voltage Vc will be then Vp minus this Vd on, which is called the on voltage of your diode D1. And using the Kirchhoff's voltage law, we can then write down that V in, which is this voltage, will be then equal to the capacitor voltage plus the output voltage. So if you write it down that the capacitor voltage is this Vp minus Vd on, then you have this expression where you also substitute this V in. Now if you now make an expression for the V out, which is the output voltage, that is then, just rewrite this, so you place everything here in blue to the left side and then flip the equation, and then you have this expression. You see directly that indeed we lose this part of the Vd on. Then you have in total this expression for your negative clamper. Now positive clamper, the procedure is exactly the same, and then you have this expression, so the only change is here from the minus sign you get the plus sign. Okay, let's now move on to our first example about the clamper circuit using the passive components. In this case we use the negative clamping. Now given this circuit we would like to determine the output voltage waveform. We know it is 20 volts peak, so 20 volts up and 20 volts down, minus 20 volts here. We have a capacitor and the diode. Everything is now considered to be ideal, but in this case we only use the voltage drop across the diode in a forward biased condition. Now we see here in this case, since it's negative clamping, that this is going down by almost minus 40, but up by 0.7, so you get here minus 39.3 volts, and you have here the positive value of 0.7 volts. You also see here the DC level of minus 19.3 volts in this situation. And this is the plot from the simulator, so you have now input voltage as set here with a specific frequency of 100 Hertz, and from the calculations we have this because this is already given in the previous slide, and this is now the maximum and the minimum value that we should have according to the calculations. But if you look at the simulation, you see here the blue line is the input, with the dark red line or this brown line is our maximum of 471 millivolts, and a minimum of minus 39.53 volts. So the diode here in this simulator is of course not ideal. It is had some model. So you see there is a small error here compared to the calculation, but still very close. Now look at the second example, considering now the positive clamp, and now the diodes are just flipped. So it's the exact same input voltage. So now we look at our output waveform. You see now it is going up almost 40 volts, but 0.7 volts down. And also we don't start at 0 volts, but we start 0.7 volts lower. And we have also here our 19.3 volts as our average value here. And again, the simulation results, you see here again the circuit, and now the blue line is our input and the right line is our output, or the curve. In this case, again, input is the same. The calculations, as we have discussed before, is this. So we can now use this and then look at the values here from the plot, and in this case it's indeed correct. But from the simulation we have the minimum of minus 469 millivolts, so not 700, so there's a error here. And there's also a maximum of here 39.52 volts and not 39.20 volts. So you actually see here 220 millivolts error in the maximum value here. Okay, this is about the situation where you have passive clamper using the passive components. Now we look at the precision clamper. Again, you're looking at the passive clamper circuit. We saw the problem of shifting down by a small value, and if this is flipped, you have a shifting up by a small value. So you have some error you don't want to have. So how can we tackle this? Again, we suffer from having one voltage drop of 700 millivolts in the signal path, and the capacitor is, in the ideal case, is not charged precisely actually to this value because of this voltage drop. And the load resistor will also draw some current and then also will discharge this capacitor a little bit, so that's also a problem again. But this situation is then a problem, but it will not be a problem and suitable for a peak input voltage, which is much larger than this diode voltage drop. Let's say this is 100, 200, maybe 500 volts. So for high power application, this 0.7 is not really that a big deal. So we can just forget about that, and diode characteristics and the actual value of the diode voltage does not matter anymore. Let's then look at our precision positive clamper circuits first. This is the circuit we already have seen in the peak detector and other rectifier precision application circuits. We see here the diode in a negative feedback loop using this operational amplifier X1. We see the capacitor and also the input voltage again, so a little bit similar to what we have before. Now this diode is placed in the feedback configuration. So this is the positive clamping. For the negative clamping, you get this circuit, so it's just flipping this diode here, just that, and everything is the same. But it can be that you don't want to clamp to a zero value or some value, but you can also have a specific value. So you can say, I would like to have a positive clamping or negative clamping. That can be also the case with bias. So that can be then using this exact same circuit here on the left side, but using here some bias, let's say 1 or 2 volts. That can be then shift your lower value up. This is also possible to place this bias voltage VB here, and then you can also create an absolute maximum value also there. So the diode is placed in a negative feedback path as before discussed. So this is the X1. So we have a superdiode, it's called, and we have now the op-amp X2 operates in a voltage buffer or voltage follower, so that the current can be supplied to the load resistor without discharging the capacitor C. And the bias voltage VB can be applied at the non-inverting input of X1, can be also done here in this circuit, to set a minimum or maximum clamping voltage at the output. Okay, let's see now our design problem. So design a precision clamp circuit, and using this circuit configuration here, we know that our extreme output voltages of our op-amps are plus or minus 8.5 volts. So we will see what it means shortly. The input voltage is given by this expression, so 2 sine 200 pi t volts. So that means our frequency is 100 Hertz, our peak value is 2 volts. A negative peak of the input voltage should be clamped to plus 1 volt. So this is an additional design criteria here. Now let's designate here this node X here. It is helpful later what it all means, the output of this operational amplifier X1. So let's look at our calculations first. If the diode is on, that means this diode is on, that means the Vx here is the voltage across this diode, since we can assume plus the Vb here, because this Vb will be also that because of this negative feedback. So we can say the Vx max, the maximum value here, will be Vd1 plus the Vb. That will be then 0.7, assuming that the diode is forward bias, plus 1 because of this 1 volt we need, and that means 1.7. So we will see later in our simulation result that this is 1.7 maximum value for our Vx. And when the diode is off, that means there is no feedback path anymore here, so this is completely open. Then the Vx, so the output voltage of the X1, will be then going in the negative part of the extreme case. That will be then VO minimum, which is in this case minus 8.5 volts. So this is then actually working as a bistable circuit. To clamp the negative peak of our input voltage to 1 volt, we need to have a bias of 1 volt, as discussed before. So we can realize this using resistive voltage divider circuit from the positive power supply we have for these two op-amps, because we need to power up this op-amps, so we can use that also. It is not really handy to get here an additional battery or additional voltage supply here, so that can be done using simple voltage divider circuit. Let's look at our simulation circuit in the Ti SPI. You see here the Vs input, the capacitor. You see here the diode D1, which is chosen as this type. We see here the negative feedback, the second op-amp, and also in the negative feedback configuration using as a voltage follower, and also our load here, and these are the power supplies 10 and minus 10 volts. You see we use 10 and a minus 10, but we have extreme values of plus and a minus 8.5 volts. That is because the operational amplifiers also consume some voltage, so we lose some voltage, so that is also needed to compensate for that. And here you see the voltage, these are the components by the way, so just a summary. And here we see here the voltage divider network using the R1 and R2. And that goes then through this VCC, and at this node, which is then this non-inverting input of this X1 or OP1, will have then a value which is the required 1 volt. So that calculation is then going like so. So VB, this node voltage, VB R2 over R1 plus R2 times VCC. Now we know what R1 is, R2 is, we just selected that in order to have here actually a ratio 1 over 10 times 10 volts. That will then result in 1 volt. So this will do the job. Okay, let's look at our simulation results here. You see the blue line is our input voltage, 2 volts peak with a 100 Hertz frequency. The red curve is our input. You see actually it's starting at the transient and then getting the situation what we wanted. And then we have also this Vx, which is this node voltage, and this is given in pink. Now, this is the circuit we have seen in the simulator. This is the minimum value we wanted, which is 1 volt. So for negative values of your input, it needs to be clamped to 1 volt, so that's correct. And it's also going up, of course, by to 5 volts. So the difference here between the minimum and the maximum of your output voltage is exactly 4 volts, as we have it here in the range for -2 to 2 volts for your input. For your Vx, we see here that it is 1.67 volts maximum, and the minimum is -8.5 volts. What we had calculated before, it was maximum 1.7 and the minimum is -8.5 volts. So the minimum is exactly the same, but the maximum, there is a small error, really small, 0.03 volts, so it's just 30 millivolts, but this is really close to what we have calculated, so we can say this is all fine. What we also see is that the diode is conducting in this region by looking at the situation for the output voltage of X1. This situation here, from this time to that, diode is conducting, because then you see that this is indeed at that moment only 1.67 volts. The rest of the time, before and after that, it is staying at -8.5 volts. So we have achieved our goal and produced our clamping of the negative peak of the input voltage to 1 volt using this circuit. Alright, for our example, considering the precision clamp circuit, we have discussed first the passive clamp circuits, 2 variations, negative and the positive clampers. We have discussed what the problems are in these passive configurations, and discuss the variations in the precision clamp circuit and discuss a design problem and verify these in SPICE simulations. If you have any questions, comments, please let me know. I will try to answer them as soon as possible. Don't forget to like and share these videos so that we can reach more people for these interesting topics. Thanks for your cooperation and see you next time in another video.